And it is the 23rd. Okay. So chapter 4. Quadratic functions. So just a quick reminder with factoring, using the box method. If I have x squared plus 5x minus 10, I can give myself a little box here to guide my work. There's going to be x's there, giving me an x squared and a minus 10 here. So I want two numbers that multiply to be negative 10. So I got to be negative 1 and positive 10, or 1 and negative 10, or negative 2 and 5, or positive 2 and negative 5. As I was watching folks do the worksheets last time, a lot of you weren't doing this part. You were just looking at it and kind of processing it in your head, which is great. That's awesome. You were doing this, you just weren't writing it down, and that's fine. And then I want these two numbers to add to be the positive 5. Let's make that a 3. That was a little goof. There we go. Make it easier on myself. And here I have one right there that works. So that tells me I have a negative 2x and a positive 5x, or a minus 2 and a positive 5, giving me an x plus 5 times an x minus 2. There's a question on the worksheet that can be done with the box method, but it looks a little different. And that question is factor 4x squared minus 81. As with many things in math, there are a lot of different ways to do this. One thing I recommended is, hey, if you see that that x squared is not by itself, if it has a leading coefficient that's not 1, start by factoring that leading coefficient out. But unfortunately, in that case, we end up with the fraction over here. And while you still can use the box method, it's a lot harder. But another thing to do is to recognize, oh, 4x squared, I could write that as 2x and square the whole thing. And I'll do my box method on the 2x instead of on the x. 2x and a 2x and a minus 81. So there's that 4x squared I was looking for. Two numbers that multiply to be 81. Well, there's a lot of different ones. I'm not going to go through them all, but I noticed that negative 9 and 9 multiply to be negative 81. And if I add those together, I get 0, which means I have 0 x's, just like there. So I have a negative 9x here and a positive 9x here. So it's a negative 9 and a positive 9. And I get 2x plus 9 and 2x minus 9. That certainly works. But you can always take these symbolic representations, and as long as you have access to something that can graph, you can convert it to a visual. So we can take our symbolic, global words, graph or pictures, numbers, and we can come down here to the graphical representation and see what we get. So I'm going to take 4x squared minus 81, and notice that I have two places where that function touches the x-axis. And those are actually going to be the two x intercepts, which tell me the factors. So before I do that for this one, I want to motivate it a little bit more. So far we have been practicing how to factor, but we really want to answer the question, why do we want to factor? If I have the expression x squared plus 3x minus 10, and I say factor this, your question might be why? I don't need to. I can use this to do whatever I want. I don't need to factor this. So there needs to be a reason why we're going to put the effort into factoring. We factor to learn about characteristics of the quadratic expression. And so in this case, expression, it's actually going to be a function. We've talked about functions, right? Where we have f of x equals x squared plus 3x minus 10, where we have an input x and it gives us an output f of x. And factoring helps us learn about characteristics of this function. Every quadratic function looks generally U-shaped, either up or down. And when you look at a graph, to me, there are a couple interesting pieces on this graph. One interesting piece is the y-intercept. That's what we talked about back in chapter 1, right? Interesting things about functions, about the graphs of functions. Y-intercept's important. This is when x equals 0. And the x-intercepts. When y equals 0. So how do we figure out from the symbolic form of our function these interesting visual characteristics? The y-intercept of a quadratic function written as f of x equals x squared plus, what did I say, 3x? Yeah, 3x minus 10 is the constant term, the one without any x's. Because if x equals 0, f of 0 would have 0 squared plus 3 times 0 minus 10. Well, that's just 0 plus 0 minus 10, which is negative 10. The y-intercept of a quadratic function is always just that constant term. Might be positive, might be negative. So this is a really useful form for figuring out what's the initial value. And I like to call this form it's often called standard form, but I like to call it y-intercept form. Oops. Because you can just read off what the y-intercept is. The negative 10 right there.
That's not the vertex. No.
Nope. Yeah, I don't get to that.
I'm sorry.
No, you're fine. You can always jump ahead. We'll come back to the vertex. That's something that only quadratic and absolute value functions have. And so right now I'm identifying kind of the things that we did generally. You don't have to apologize. I like those questions. Okay, how about x-intercepts? X-intercepts are when the output equals 0. That's when I have something like x squared plus 3x minus 10 equals 0. X squared plus 3x minus 10 equals 0. That happens when x equals -5 and when x equals +2. Which is very similar to the factored form. When I factored this, I got x plus 5 and x minus 2. Exact same function because factoring doesn't change whether it's the same function. The x-intercepts of this function are the opposite of what you see when you factor it. Because what happens when x equals -5? -5 plus 5 is 0. 0 times anything is 0. And when x is 2, 2 minus 2 is 0. 0 times anything is 0. So the reason we factor is to find out when y equals 0, i.e. the x-intercepts. Which is very helpful if you're working in any sort of physical situation. It's really nice to know when the output's going to be 0. Right? If you're throwing a baseball, it might be nice to know when it hits the ground, when the height is 0. If you're running a business, it might be nice to know when your profit equals 0, right? When you break even or when you've gone too far and now you're going to start losing money. There are lots of times when you want to know when the output equals 0, x equals -5, and x equals +2. Make the function 0. So these are the x-intercepts. Let's do another one. All right, so solve negative x squared plus 7x minus 12 equal to 0. We want to know the x values that make this function 0. Oh, I am really asking what are the x-intercepts? And I find this by factoring, or find them by factoring. I'll use my box method. I'll pull that negative out first. So I get negative x squared minus 7x plus 12. And when I box it, I need two numbers that multiply to be 12 and add to be -7, -3 and -4. So I have x minus 3 and x minus 4. I factored it. If I want it to equal 0, that means x has to equal 3 or x has to equal 4. And these are the solutions to that equation because these are the x-intercepts.
We have that homework.
Uh-huh.
And I did it that way and it was wrong.
Well, let's
It was
take
6.
this exact question.
Yes.
Yeah, I'm happy to look at that exact question with you. Yeah. But I think I did this right this time. I'll do it wrong another time. I mean, I already did it wrong earlier, right? I put the wrong number there and I was headed down the wrong path. Happens all the time. Let's just take a quick look. We had a minus x squared plus, was it plus 7x? Yeah, plus 7x minus 12. when x is 3, and when x is 4, my output is 0. So I've solved it. Desmos is really nice because it allows you to click on important points. What do you think that point's going to be? Negative 12. There it is right there. Negative 12. Yeah. So not only hopefully does this help you kind of connect between the symbolic and graphical representations. Let's solve 13x squared plus 92x minus 144 equals 0. Who wants to do that using the box method? Nobody said yes? Good
Wants to do
answer.
what?
Who wants to solve this using the box method to factor? I sure don't.
I don't.
Yeah, but we don't have to because we know that this will be solved when x is an x-intercept. So what I'm really asking for is, what is the factored form? But I can get that using Desmos, using my graphical representation. I switch it from the symbolic to the graphical representation. 13x squared plus 92x minus 144. There we go. Sure, it's a decimal approximation, but it's going to be good enough if I'm running a business and I need, 1.319 thousand items. I don't care about those extra 28, one way or the other. They're crickets, right? 28 crickets, more or less, who cares? It's close enough. So I can switch to the graphical representation. I'm here in the symbolic. 13x squared plus 92x minus 144. I want to get it over here to the x minus and x minus form. I'm going to work through the graphical to help me. And when I do that, I know you can't see this, but you did see the graph. I see that this is x plus. First, let me say, on my graph, I see that I get a negative 8.4 and a positive 1.3. 1.3. So that means I have an x plus 8.4 times an x minus 1.3 with a 13. And those are my solutions, negative 8.4 and positive 1.3. I think it's really important to be able to factor quadratics by hand using the box method or some other method when they're like this. It's an important skill. But if you got this, something like this, it's also important to recognize, use the tools that you have on hand. And if you can use a graphing system to help you, use a graphing system to help you. It's like, I personally think it's really important for people to learn how to ride a bike. It's fine if you don't. It's enjoyable, it's good exercise, it gets you to point A to point B, it's fairly economical. But I'm not going to ride from here to Eugene. I might be able to, but that would be tough. I'm going to use the tools I have available. I'm going to drive or take the train or some other method. Okay. I'm not going to ask you on the final, for example, to factor something like this by hand. I'm not going to ask you to solve this equation on the final because I would expect you to use a simple graphing calculator like Desmos, and not all of you are going to have one, right? Some of you have a scientific or graphing calculator, but some of you don't. I don't need to ask you to do that on the final. I'm gonna want you to be able to do something like this on the final by hand. Speaking of vertex, if we look at a general quadratic function and we identify those graphical points of interest, we've got the x-intercepts, right? The x values where the output is 0. We've got the y-intercept, the initial value or the point when x equals 0. And we also have the turning point. It's a maximum or it's a minimum, depending if it opens down or opens up. And we call this the vertex. Also super important. If this is a profit graph, you probably want to know how to maximize your profit. If this is a firework, you probably want to know how high that firework's going to go so you can explode it at a safe height. There are, let me see. I'm just seeing what I'm asking you to do. Yeah. I think I asked you to find vertex. Yes, I do. Okay. There are a number of ways to find the vertex of a quadratic function. But before you go about finding, you should always ask me or anybody else, but why? Why do I want to find it? So why would you want to find the vertex of a quadratic function?
So you wanna see what that maximum height?
Exactly, because it's an important characteristic. You want to find the maximum, or maybe you want to find the minimum. That's an important characteristic. Why? It is the max or min. Okay. So the easiest way is graphically. Find the vertex of, let's do negative x squared. Hold on 1 second again. Plus 4x minus plus 5. Plus 5. All right, find the vertex. This means find the max or min, depending on if it's going to open up or open down. Does this one open up or open down?
Down.
Down, because as x gets bigger, your values are going to get more negative. Yep. All right, do it graphically. Minus x squared plus 4x plus 5. There's my vertex. Says it ideally will always be as simple as that.
When you're using the graphical method?
Yeah.
Yeah.
Yeah. Now I picked it, I had to do some thinking so that there would be integer values, but even if they aren't, it's where it turns around, and on Desmos, you can always click on that point, which is nice. So I got, just to sketch it really quick. That point right there, xy equals 2, 9. Let's find the vertex of negative x plus 1 times x minus 5. And we're going to do this graphically as well. So this one is in factored form. Oh, but it's the exact same function, and I did that on purpose. You can still find it graphically even when you're given factored form. It's still 2 comma 9. And look, there are my x-intercepts. The -1 corresponds to the x plus 1, and the +5 corresponds to the x minus 5. And it's opening down, which is why there's a minus on the front.
No question. Can you find the vertex by taking the 2 points and, in the two? Yes,
Yeah,
I'm sorry.
no, it'd be great. Oops. So every quadratic function is symmetric right about its vertex. You could flip it over, which means it's also symmetric between the 2 x-intercepts. The x coordinate of the vertex is always going to be halfway between the 2 x-intercepts. So that's my way of solving it symbolically. In fact, a quadratic function or a graph with the function 2 is symmetric across the vertex. This also means that it's symmetric across the y or the x-intercepts and across the x-intercepts. So if you want to find the vertex from the factored form, you start by finding the x value halfway between the x-intercepts. My x-intercepts are x equals -1. I'll just put this on a number line, and x equals 5. And right between them is a point x equals 2. 5 plus -1 over 2 is 4 over 2, which is the x value, right? Just add those 2 x-intercepts, divide by 2, that'll get you the halfway point. Then plug x equals 2 into the formula. Minus 2 plus 1 times 2 minus 5 is negative 3 times -3, which is 9. And that's the y value. You can do it completely symbolically, especially when you have the factored form. That's the easy way. I still think graphically is easier. And I think the more important thing is understanding what the vertex tells you. Tells you the maximum point, and also when you reach that maximum point. The maximum is 9, and you get there when x equals 2. Yeah, so your worksheet has some functions of differing complexity, and I ask you to find the vertex, and if you want to try it by hand, that's great. But I think a lot of times you're just going to want to switch it to a graphical representation. Math that I want you to learn in this part is understanding to figure out these characteristics, use a graphical representation when you can, because that's helpful. A couple more ideas. You can find the vertex starting with the y-intercept form. I had a minus x squared plus 4, is it plus 4x? Yep. Plus 5. That's there. In general, this y-intercept form, we could represent it as ax squared plus bx plus c. That's the most general way to write down a quadratic function. In our case, a is -1 because there's a minus, b is 4, and c is 5.
We call it standard form?
Yep. I call it y-intercept form because there's a
Oh.
y-intercept, but yeah, standard form. So C, that tells you the y-intercept, awesome. A tells you that it opens down. B is interesting, but not something I'm going to talk about in this class. If you take Math 111 with me, you'll get to explore what B tells you about a function. The x-coordinate of the vertex is minus b over 2a. If you ever heard of completing the square, this is what you get when you do that process. But you don't ever have to do that process as far as I'm concerned. In this case, it's going to be minus 4 over 2 times -1. Well, that's minus 4 over minus 2, which is 2, just like I thought. So you can find it directly from the formula using the minus b over 2a, and then you get the y-coordinate by plugging that in. Minus 2 squared plus 4 times 2 plus 5 is -4 plus 8 plus 5, which is 9. So you can do it symbolically. I'm not going to ask you to find the vertex of a quadratic function symbolically on the final, but I will ask you to interpret what the vertex tells you. If you want to find the vertex, as far as I'm concerned, use a graphical method, because that's really what it's telling you the turning point, and that's a very graphical concept. Okay. So in summary, there are 3 ways to write a quadratic function. The first way is y equals ax squared plus bx plus c. I call this y-intercept form. You probably know it if you do as standard form. There's my y-intercept right there, the c. The second way, we still need that a because that's our leading coefficient that tells us if it opens up or opens down. X minus x1 times x minus x2. This is x-intercept form, often called factored form, because the x-intercepts are x1 and x2. You can just read them right off. If you see an x plus, it means the x-intercept is a negative number. And the third form is called vertex form. And I don't like it, but they use H and K. I call this max min form. Usually you'll see it as vertex form. The max or min is the points x, y equals h comma k. But I'll do it with this example. You can see it. You can always go from one form to the other. The easiest way to do that is graphically. It is possible to do it symbolically or numerically. If you crunch some numbers and you figure out what x values get you to 0, you found the factored or the x-intercept form. Okay, so our example was minus x squared plus 4x plus 5 is the exact same thing as minus x plus 1 times x minus 5, which is exactly the same as minus x minus 2 quantity squared plus 9. The y-intercept is 5. The x-intercepts are -1 and 5. Happens to be the same. And the vertex is xy equals 2 comma 9. All right, with that in mind, let's come back to 4x squared minus 81. And I want to solve 4x squared minus 81 equals 0. And we did that box method. It was a little clunky. You had to recognize you could write 4x squared as 2x quantity squared. If we do this graphically, though, we're really finding the x-intercepts. All right, so that 4 is going to live out there, but we're going to find a couple different factors for it. So we come over here, Desmos, 4x squared minus 81, and that's all the time it took to find that the two x-intercepts are negative 4.5 and positive 4.5. There's the x-intercept corresponding with negative 4.5, and there's the x-intercept corresponding with positive 4.5. Now there is another way to solve this, which is called the square root method. It's not a better way, it's not a worse way. It's just picking a different tool from your toolbox. It's going to work on some, it's not going to work on others. If I have 4x squared minus 81 equals 0, and I'm going to solve this. We did it graphically, which is great. Earlier, we did it by factoring using the box method, which was a little laborious. Here, I'm just going to recognize, oh, I only have one term with the x's, so let me isolate that. And I get 4x squared equals 81. And how do I unwrap an x squared? I'm going to take the square root of both sides. So I take the square root of 4x squared should equal the square root of 81. And I grab my calculator and I find out the square root of 81 is 9. And the square root of 4x squared is 2x. So x equals 4.5 because 9 over 2 is 4.5. It also works, but I made a mistake. Does anybody see the mistake I made?
Plus and minus.
Exactly. There are two x-intercepts, and that's very obvious from the graph. But I only came up with one solution. That's because when you solve using a square root, you also have 2x equals -9. Because when you square -9, you get 81. So the square root method should give you a plus and a minus. And that's something that you have to remember as you do it.
Is this class getting smaller or?
No, well, it's our attendance is not as, shall we say, strong as before.
Okay.
Yeah, but no, no drop in enrollment. I love it that you are here. I think all 6 of you are benefiting from being here. That's, it's hard for you to know because you can't live in two realities at the same time and then compare them. But that's what statistics tells us is you take a large enough sample of people and you apply different experiments to them or different conditions. And generally the students who come to class tend to do better than the students who don't, except for those few students who probably didn't need to take the class in the first place. And so I'm glad that all of you are here. I hope it's helpful. All right, so can I do the square root method very easily on this guy? No, because we got that 4x piece in there, right? It doesn't work very well unless the only x's come as an x squared. So this is what I mean when I say the square root method is a tool. Sometimes a tool can be useful, sometimes it doesn't, and part of the math is deciding when it's useful. And finally, there's one other method that's done completely symbolically, which is the quadratic formula. Which says if I have any function, any quadratic function, and to represent that it's any quadratic function, I use ax squared plus bx plus c. And I solve that equal to 0. The solutions will be x equals minus b plus the square root of b squared minus 4ac, all divided by 2a, and x equals minus b minus the square root of b squared minus 4ac, all over 2a. So if you have the A, B, C as numbers and you just want to crank it out with numbers, Gabe mentioned this on Monday, Gabe prefers this method. Cool, awesome. I don't. I recognize that in the real world, you're rarely going to have a quadratic function that can be factored easily with the box method. The quadratic function is the tool that always works and the tool that usually takes the most amount of time, which is pretty accurate. I mean, if I wanted to get from here to any point in the continental United States, the method that would guarantee working would be using my feet. Right? I'd have to stop to eat and sleep. I might have to swim, but I could get to the top of the Continental Divide. I could get to Florida. Not very efficient. A car would be a lot better, but a car's not going to get me to the top of Mount Hood, right? So this is the walk it method. It will always work. It's very rarely efficient. There are almost always more useful tools. If you have something like this, square root method is great. If you have something like this and you're going to do it by hand, the box method's probably great. If you have any function at all, graphical method, always good, but it might only give you approximate answers, which are usually good enough. So let's just use this on ours. We had minus x squared plus 4x plus 5. So the A is -1, the B is 4, and the C is 5. So using my formula, I'm going to get -4 plus the square root of 4 squared minus 4 times -1 times 5, all over 2 times -1, which, as you see, is a lot of numbers to carry around. That's -4 plus, that's 16, that's plus 20, and that's -2, which is -4 plus the square root of 36 all over -2, which is -4 plus 6 all over -2, which is 2 divided by -2, which is -1. And that was one of our x-intercepts. And the other one is similar, except instead of adding 6, it's subtracting 6. So the other one is going to end up being -4 minus 6 all over -2, which is minus 10 over -2, which is +5. It works, but slowly. I would certainly prefer to use a graphical method whenever I could, because a graphical method will always tell you the x-intercepts. And the difference is it's going to give you a decimal approximation if it's not an integer or a simple fraction. At least in Desmos. There are calculators that can convert decimals to actual fractions to give you the exact answer. There are even calculators that can say, well, this would be close to this number with the square root, but okay. Now, let me ask you again, why do we bother with all of this with quadratic functions? Why do I bother factoring? Why do I bother finding x-intercepts and y-intercepts and vertices?
Well, with the highest profit it
Is because quadratic functions model physical situations, profit,
okay.
gravity, populations, things like that. And those characteristics tend to be the important ones. We find x-intercepts because that tells us when the output is 0, which is usually good to know. We find y-intercepts because that tells us what the output is at our initial, which is usually good to know. And we find vertices because that tells us when our output is a maximum or a minimum, which is usually good to know. Okay. There might be a couple more skills in here that you got to work on, but I think that's about it. So let me stop the recording.